Hello and welcome to Return. I am Emmy and today we are going to pull back the curtain on one of the biggest mysteries in machine learning, the black box model. Imagine you have built a powerful model that predicts whether a bank should approve a loan or not. It takes in an applicant's data like income, credit score, age, and so on, and gives a simple yes or no. But what if it says no? Why did it make that decision? Was it the low income, a past default, or something else entirely? This is the black box problem. We have a powerful tool, but we don't fully understand its reasoning. This lack of transparency is not just frustrating, it can be unfair, unsafe, and a huge barrier to trusting our AI systems. But what if we could ask the model why? That is where Shap comes in. Shap, which stands for SHapley Additive Explanations, is a groundbreaking approach from game theory that helps us understand the output of any machine learning model. It connects what we want, a fair explanation, with a solid mathematical foundation. So how does it work? Let us use an analogy. Imagine a team of 3 players, Alex, Ben, and Chloe, playing a cooperative video game. Their final score is 100 points. The question is, how do we fairly distribute those 100 points among them? Who was the most valuable player? We can't just look at their individual skills. Maybe Alex is great alone, but Ben and Chloe have an amazing synergy that boosts the score. To be fair, we need to consider every possible combination or collision of players. Shapley values, the core of Shap, calculate each player's average marginal contribution across all these combinations. It sounds complex, but the idea is simple. It measures how much a player's presence changes the outcome on average. After doing the math, we might find that Alex contributed 40 points, Ben 25, and Chloe 35. Now let us bring this back to machine learning. Instead of players, we have features like income, age, and credit score. And instead of game score, we have the model's prediction. Shap calculates the payout or contribution of each feature to that final prediction. The core idea of Shap is beautifully simple. It states that the prediction for any single instance is the sum of a base value and the Shap values for each of its features. The base value is simply the average prediction over the entire dataset, what the model would guess if it knew nothing about the current instance. Each feature's Shap value tells us how much it pushed the prediction away from that base value. A positive Shap value pushed the prediction higher and a negative one pushed it lower. Together they explain exactly how we arrived at the final result. Alright, enough theory. Let us see this in action. We are going to use the popular Shap library in Python to explain a model trained on California housing dataset. Our goal is to predict the median house value in a given area based on features like median income, average number of rooms, and so on. First, let us set up our environment. We will need Scikit-learn to load the data and build the model, XGBoost for our powerful black box model, and of course, Shap. Now let us import the libraries, load our data. We will also train a simple XGBoost regressor model. This model is known for its high performance but can be quite difficult to interpret on its own, a perfect candidate for Shap. Great, so we have our trained model. Now for the magic. We create a Shap explainer. This object takes our model and wraps it in a way that allows Shap library to probe it and calculate the Shapley values for us. With our explainer ready, we can now calculate the Shap values. We will do this for our test dataset. This might take a moment as Shap needs to evaluate the model many times to get those fair contribution values for every feature of every data point. Done. We now have the sharp values, but numbers alone are not very intuitive. The real power of the Sharp library comes from its amazing visualizations. Let us start by explaining a single prediction with the force plot. Here it is. This is a Sharp force plot. Let us break it down. The base value, around 2.07, represents the average predicted house value across all homes in the dataset. The model's prediction for the specific home is 2.84, so higher than the average. Now the real question is, what features are pushing the prediction up or down? Look at these colored bars. On the left in red, we have got features that are pushing the prediction up, making the house seem more valuable to the model. Median income, mid-inc, equal to 4.804, meaning this neighborhood has a relatively high median income. Then we have average occupancy of 1.798, suggesting fewer people per household, often a sign of larger or less crowded homes. And lastly, the biggest contributor, longitude, minus 122.1, which places this home closer to the coast, a factor that usually boosts value. Features in blue, like latitude and average rooms, are pulling the prediction down, while latitude, a location-based feature, does have a negative impact. It's not the strongest. That title goes to average rooms, which has the largest downward influence in this case. All these forces, red features pushing the prediction up and blue features pulling it down, create a kind of tug of war. And the result? Our final predictions lands right where that balance settles. This is incredible for a single prediction. But what about the entire dataset? How do features behave on a global scale? For that, we use a summary plot. This might look like a colorful mess at first, but it is one of the most information-dense plots in machine learning. Let us decode it. On the y-axis, we have our features, ordered by their overall importance. Latitude and longitude are the two topmost features, meaning that they have the largest impact on the predictions. Each dot on the plot is a single prediction from our test dataset. Its position on the x-axis shows its sharp value. Dots to the right have positive sharp values, pushing the prediction higher, and dots to the left have negative values. Now, the color of each dot represents the original value of that feature for that data point. Red for high values and blue for low values. So what does this plot tell us? Look at mid-inc again. The red dots are all on the right side and the blue dots are on the left. This tells us a clear story. High median income consistently leads to a higher predicted house value, and low median income leads to a lower one. This confirms our intuition. Now pause the video here and look at average rooms feature. What story is it telling you? Welcome back. You probably noticed that for average rooms, a higher number of rooms also pushes the prediction up. But look at latitude. It is a bit more mixed. But we see a clear trend where high latitude, red dots, more northerly, tends to have a negative sharp value, lowering the predicted price. Finally, let us look at one more plot, the dependence plot. This helps us isolate the effect of a single feature and can even reveal interesting interaction effects. Let us plot the dependence of mid-inc. Here, x-axis is the actual value of the median income and the y-axis is its sharp value. We can clearly see the relationship we saw in the summary plot. As median income increases, the sharp value also increases, raising the predicted house price. Now look at the color, that is av-occup or average occupancy. Blue means fewer people per household and red means more. Notice the trend. For a given income level, the redder dots, higher occupancy, tend to sit higher on the y-axis. That means the model is assigning more predictive power to income when households are more crowded. In other words, Income matters more in the model when average occupancy is high. That is an interaction effect. One feature shaping how another behaves. And this isn't a causal claim. We are not just unpacking what the model has learned. And while the trend is clear, it is not perfect across all income levels. So let us recap. We started with a black box XGBoost model. By applying Shap, we were able to dissect its logic. We explained a single prediction using a force plot. We understood global feature importance and effects with the summary plot. And we even uncovered subtle interaction effects with a dependence plot. We have transformed our mysterious black box into a transparent glass box. This is the power of explainable AI. It allows us to debug our models, ensure they are fair, comply with regulations, and most importantly, build trust in the systems we create. Thank you for joining me on this journey into the heart of model explainability. I hope you feel empowered to open up your own black boxes. If you found this helpful, please like, subscribe, and share it with someone who might be curious. Until next time, keep exploring.